Today, I'm going to talk about the GoldSim implementation of a snow accumulation and ablation model called Snow 17. It was originally developed by the National Weather Service River Forecast System, NWSRFS, apparently. Um, and there is a link to a document all about this model. And I'm going to scroll down and it is not in this version of the model. But anyway, when you download, I'll show you. I'm going to walk through it and I'll show you the link and we can even visit it. Also, I took a picture of it because I wanted to include this eventually in the model. But this diagram, which, oh, there it is. It's hiding. There's the reference. I'm just going to paste this here. Okay, that came in a little on the big side. So now I'm doing some GoldSim modeling on the fly here. I just need to change it so that this image has a locked aspect ratio so that when I resize this thing, it resizes properly. But I just realized something else. I kind of went against what I tell people to do, and that is when you first copy an image, the you get the best results, honestly, if you paste it into PowerPoint first. There are other tools you could use, but everybody has PowerPoint, I think. So it's easy enough just to describe it this way. So I'm pasting it in. That's a lot better. It will look better too if I resize this. There. Okay, great. All right, so anyway, this diagram is essentially covering the components of the model that we'll be talking about. Before I go into what the model does, I want to show you kind of a real world scenario, and I apologize for the mess that you see in this model. It doesn't look very well organized, and it's because um, I was throwing this together for an example to show that I just wanted to know, can I calibrate a Snow 17 model in GoldSim? And so that was the question I had. So I went ahead, I thought I should probably know that. I should probably try it before we post this on our website. So I did, and I don't think I'm done with the calibration process yet. I looked at the results, and I think we can do a little bit better, particularly because I chose a terrible time frame. So let me back up a little bit and show you that. So originally, I had this model set up to run. Oh, this is actually what I had started. 2008 to 2014 was my calibration period. And so what I did is I said, okay, let's put Snow 17 built in GoldSim. This is in our library, and I can show you later where you get that in our library. But I just copied and pasted it into a container, into this model. And then I also put in um, some rainfall data, and I split this. I put a picture of a watershed here. This is the watershed I'm modeling. I have gauge data at the tail end of this, so I can compare runoff in this watershed. And this is a very snow-dominated watershed, also. So that also works well with this. Anyway, so I developed this model. I delineated this watershed, and I think I split this watershed up into three zones. Uh, so with Snow 17, it's important to understand how you divide up the area. So it does account for the area of the individual catchments that you divide your watershed up into, but it also needs to know, very importantly, what is the elevation um, of this area. And so you have to think of it in bands. You have bands in your watershed, elevation bands. So if you took a contour map, then what you would see in here is you would see one band that's just the lower areas of the watershed, right, down by the river. And then you would see another band maybe halfway up the slope and then going up into the top, and then the top band all the way up in the top. So we do that for obvious reasons because the snow is melting at different rates at different places and it's accumulating differently. And it just makes more sense to divide it that way. And it's still pretty simple. So this watershed was divided into three. zones. And I didn't want to go too much detail into how to build this watershed model, um, because it's kind of a different topic. I mostly want to talk about the snow model, but just so you understand how I implemented this. And the purpose of this presentation is to help you understand how you can put this model, or you can work with this model in your for your work, which would probably involve runoff or some sort of flow calculation. I would imagine most people using it. So that's what I was doing here. And okay, so what I do is I just built this overall model with the picture and all this description in here. And then in the system model, I have all the components of the model to calculate runoff. There's also a reservoir, so it's more complicated, but we're just ignoring the reservoir, and that's down at the downstream end, but we'll just ignore that for right now. But there's a river gauge upstream of the reservoir, so we can look at the flows compared right there that we calculate. And so what I do is, I was thinking of eventually having a weather generator, where you can put in a stochastic rainfall and temperature, min-max temperature, which can then drive your snow model, and also you can calculate evaporation rates and then estimate the effect of those two things on your runoff in a snow-dominated watershed. So that was kind of the goal here. But before I could do that, I needed to be able to calibrate the model, so that I could just start throwing random, random rain events, random dry periods, and then calculate random outputs from it. So I needed a calibrated model. And so anyway, so in the model inputs, let's see. Yeah, so what I had to do, and I don't know if this is really necessary, but this is, I think, because I wanted to have a user interface where you could put the information in, but I don't know if this is such a good idea. I moved all of the runoff input data to the model inputs. So if you look up at this top bar, maybe the browser is the best way to see this. And also I'm using versioning. So I think what would be best right now would be to create a new version. And this is webinar. And this also uses some new functionality that you won't see until the next version. But anyway, okay, so over here we have all of our top containers. Let me collapse them so you can kind of see how the model's all built. If we go, you see there's system model, and in here we calculate evaporation, snow, runoff, all of those things, right? But then up here, we have a separate container at the root level, all the way at the top, called model inputs. If you really need to have model inputs, then that's fine. But lately I've not liked this very much because it really removes you from the components that you're modeling, by having to go back and forth, so you could clone these elements so that they exist here and over at the other place. That's one way to get around that. Anyway, these are all of the inputs for the AWBM model. This is a runoff model, estimating runoff with a precipitation input, that those of you, especially in Australia, would be familiar with. But I moved all of the inputs over to here. I did that for, it looks like, for the other models as well, snowmelt and evaporation inputs. Anyway, so they're all in one place. And then we go into the system model, and then we calculate rain if we're doing stochastic, but for calibration purposes, we'd just be looking at a time series. And so that would be in here. I just swap out a time series precipitation with the stochastic rainfall generator, which is a whole different subject. But if you wanted to produce stochastic rainfall as an input to your snow accumulation model, you could do that, right? Instead of having a time series. That's ultimately where I was wanting this to go. But anyway, so I'm referring to historic measured precipitation daily values and also temperature. Those are recorded and those are put in a time series and they drive the models essentially. And so here's snow 17. We calculate the snowpack over time, and then when it melts, it adds to the runoff to the existing rainfall if there's rain, and so on. All of that is captured. We have evaporation we're calculating, also using to calculate the losses in the system, and then I calculate a runoff, and then at that point, if I go up a level, you'll see I've got a calibration page here in which then we can do the calibration. Okay, so when I run this model, then I can look at a comparison of simulated versus versus runoff. They're calculated. Sorry, simulated versus historically measured stream flows there. And it looks like somebody has a question. Oh, no questions. Okay, looks like we're okay. But feel free to ask a question if you do have any there. Okay, so that's incorporated. So now you can kind of see how it might be incorporated. And the nice thing with this model is then you could look at maybe a reservoir over time. So here's the operation of this reservoir where the flow's coming in. It's the red line in water level. So anyway, just now imagine once you have a calibrated model for that particular location, then in theory we should be able to throw some random forecasting into this to see how it might handle droughts or whatever. So anyway, that's how it can be incorporated, but let me talk about the model itself. So now what I'll do is I'll open just the Snow 17 model because there's some things you need to know about it if you're going to incorporate it. I don't think I need to save that. Okay, hopefully not. All right. So this is oh, I'm going to, yeah, I have the notes turned on. Okay. So in this model, I use the note pane so that I could have more space for the model elements. So I put the note pane, just dock it over to one side. This works well if you have your, a landscape view screen turned on, like I do right now. Then everything kind of fits well. Anyway, so the main inputs to Snow 17, and here's the whole model right here. It's this one script element. Why did I do it that way? Well, it turns out it's just the way the calculations go. It's very procedural. It just kind of walks down through a bunch of equations and it works well. You can access the code on GitHub. It's written in Python, I think. That's what we translated it into GoldSim from. And so anyway, there it is. It's all in the script. I'll talk a little bit about that in a second, but the inputs to it are the main ones. Average temperature, so that's average daily. Usually you might have like min and max daily temperatures, right? So you have to take the average of those. That's the input. And then daily precipitation values. That's daily cumulative each day, the cumulative rain. And so that's an input. So we do have a model where you can generate those randomly, which is that's a previous webinar I did. And so that could be the input to this model, right? Then you could see it stochastically. But anyway, for a historic run, which is what this is, what I had in there, you have just these two time series. You could also put in observed things. Like I happened to build this model in an area where we had a snow depth meter, a snow depth gauge built up there. It's been observing snowpack for years. Actually, for the period of record I ran, 2008 to 2000. Well, actually, it's still running today. But anyway, this is a good place. It's always good, right, to put all the observed information in that you can find in there. And so I have a place for that. And then there's some constants that you need. So you need the elevation zones. That's really important. So this is 3 different zones. This is the mid, the average elevation for each of the elevation bands. So the peak at the top of this watershed might be maybe 8,000 feet or something like that. But We stopped it at 6,700. Sorry, we took the average of the band. It's 67. Um, and sorry, I'm starting at the bottom. That's the bottom, and then the top is 8,000. Sorry about that. So at the third zone is the highest elevation zone, and so the top might actually be 10,000 feet. That actually sounds more right. So the top might be around 10,000 feet, but the average is 8. But there all might only be a tiny little bit of the watershed that's up that high. So anyway, averaging, right? It's all lumped conceptual model. That's what this is. Um, but it does incorporate functionality that represents the physical processes that actually occur, and you can read about it in the documentation there. Um, and here's the link down at the bottom of the page. Anyway, so you divide up the watershed into those zones. You need to specify a latitude on the Earth, um, and then you need a reference elevation, and the reference elevation is of where the snow gauge is, and because that's where these measurements are coming from, is the snow gauge, and that's what the concept is here anyway. So my average temperatures, my daily precipitation, those are being measured at this gauge at a certain elevation, and that elevation is written right here in this element. And that's what the model uses to then compute the differences in temperatures and so forth in the other elevation bands. That's how it gets those numbers. Okay, so let's talk about the script element. So the script element, if you've never used it before, when you open it up, you'll see it's just blank with a bunch of green and white lines all the way down. And I've got a bunch of inputs in here, but it's just blank. But you're very controlled in what you can put in to the script element. You have to use the insert command down here, and then this is the only way to put lines of code in. Now you can type whatever you want in your comments, but most everything else, you're in a very controlled environment. You can't really go outside of that. You can't write driver software or anything in here. There's nothing else. You can't refer to really anything outside of GoldSim at all. No, I mean you cannot at all. And you can only reference element names that are accessible and within the correct type from within the model. And so you can see what's feeding this script element, all of these inputs right here. And then we have this kind of curious thing over here on the side, and I just want to make sure everybody can still hear me. I heard a little beep, and so I wasn't sure if I went silent, but it looks like it's okay. Somebody asked, was there snowpack data to calibrate to? And the answer is yes. Yes, that's why I built it for this watershed, because there is a snow gauge in this watershed. Yep. And they did it. They observed the snow water equivalent. That's what this SWE is. They had that measured. So I know that's not really very commonly the case, right? And it's pretty rare to have, but that's why I built it. That's why I built this model for this watershed um, there. So hopefully that answers your question. Okay, so so it turns out that a script element is a state element. Okay, so what's a state element? A state variable. It's something that can carry state forward over time. A really good example of that is an integrator. So if you get an integrator into a model and you say, I want to just add every day, I just want to add one. I want to add one thing every day. So you just put an input like this, right? You put that input in there, you run the model, and you expect it to be 101, probably. Let's see, 100. Oh yeah, because it didn't count the very first day. So this integrates one value over each day for 100 days. That makes 100. And you can plot it, right? And you can see that how it's going up over time. And so all you're doing is you're just adding a value to its current. Every time step, you just add a little bit more to it. Right. In our case, we just add one to it every single day. Well, it turns out that means it has state because it knows what its value was the previous update. It keeps track of that. That's called a state variable. Another state variable that we have in GoldSim, or a state element, is a script element. In a script element, just like an integrator, you give it an initial value. So we can say, what's the initial value here? Well, let's say the initial value is 10. And then what we could do is we can say, well, I want to excuse me, I want to add one to that value every time this updates. And so you can do the same thing like you did with an integrator by referring to its own state. And its own state is the main output called result. So if I look at the output port of the script element, you see it has this output. It's called the same name, but you can refer to it in two different ways. So I could put in an assignment here, and I could say, you know what, I want to reassign the value of the result, which is itself, the script. I want to reassign it to, and then I could write tilde, and tilde is how you, I didn't want this to become a full lesson on how to use the script element. There's a lot of things you need to learn about to effectively use the script element. So I don't want to go too much into this, but it is important to note that you need the tilde symbol like this to access variables inside the script. I don't have any currently except one, and that's the result. That's this output of this thing. But to refer to any of those inside, then I put the tilde symbol. You can see there's a whole bunch of other names here, but these other names, these are all just run properties of the these are all just run properties of the model, so they're all built in. But anyway, if I type in result, it refers to itself. You can see it says, oh, I already know I'm 10, but I could say, let's add 1 to it. So every time the script updates, it will add 1. And it doesn't necessarily mean it updates once per day. It does just by chance right now. But anyway, so it just works. But if I hover over it, in this case, it says 111. And that's just because it updated on time 0 as well as the final value. That's why it's 111. But it started out at 10 and then it went up from there. But you can refer to its own result, and that's a good way to have memory. So a lot of programs out there, they hold memory as they walk through, for example, an iterative structure, like an if for loop, like in a for loop. Oftentimes you have to carry things forward. You have to carry variables forward, and because they impact its value on the next update. And so a script element can allow you to carry values forward in time, not only just in it within the script value itself, but you can carry it forward in time as the script closes and then reopens and updates all of its calculations again. It's kind of like it's got its own little memory bank, and it can store that value. But the cool thing is there's a workaround where you can store a number of values, not just one value. And I do that using an array label set. So let me show you what I mean. So if you go to model and then you go to array labels, you'll see here I have a snow 17 vars array label set. And what I do here is I say, these are all the things that have memory. They have to carry forward. And these variables, they are, AIT is antecedent temperature index. That's right. I forgot about that. And so that's a value that's calculated in the script, but it needs to carry forward through time. I need to keep track of what it is as we're walking through time. Same with heat deficit and water equivalent in ice and liquid water held in the snow. So there's the ice component and the liquid component it keeps track of. So I need to keep track of all 4 of those things. And what I mean is, as I walk through time and as this script element closes and reopens and updates, because every time step it just starts fresh again. That's what every element does. But the state variables are special because they remember what they calculated the last time step. So that's why I just wanted to make sure that's clear. You're clear on that, because it's a really valuable way to make use of holding a whole bunch of values that you want to carry forward within one script. And there's a workaround, and that is to make the make the result, the script itself, hold a list of outputs. And that's what I did. It's now holding a list of Snow 17 variables, antecedent moisture index, or whatever that was, the heat deficit, etc. Those things, it will keep a value under each of those now on each time step and carry those forward. And so the reason that's really nice is because you scroll down here enough, you get down to a point in this script, and it says initialize the state variables. And this is where on every time step, it goes in there and says, well, what did I used to be? Okay, get that one. And now let's start working with that one. That's how it works. And so it needs to do that with all of those variables. And then as you continue down through the process, then it calculates a whole bunch of other things. And it's not like a rocket science kind of it's not a numerically intensive algorithm here. It does have a lot of lines though, and so what it means is it's a complicated set of equations, a lot of if statements, depending on a lot of different things, depending on the state of a lot of different things. So it just lends itself very nicely to a script element. Could you imagine building all of these as selectors with all these if statements? It could certainly be done, but it would be probably harder to walk through, I think, in this particular case, just because of how these equations go. But anyway, once we get all that information, then we can calculate the snow water equivalent over time. And so that's what this model does. If you click run, then you can look at um, which one do we want to look at? Maybe this one. This is all the zones. So this is zones 1, 2, and 3. So you can see 3 is the high elevation zone up here where the snow melts at the end, the last. Um, and so yeah, so that's the model. So how would we hook this up to your model? Well, you need temperature, average daily temperature. And again, this is all assuming daily time steps, and I have no idea how this would work in any other case, hourly or monthly. I'm just not sure. I've never done it, but it works well in daily time steps. But you're certainly welcome to look into, changing the time step if you want. Anyway, so daily time steps. So that's what you need for the inputs, and then just the latitude elevation zones. And so then the question is, well, what if I don't have a snow gauge nearby? Well, one idea is to, if I calibrated this for this watershed, I might, we might be able to do another watershed, down a ways, and then maybe our watershed is in the middle, or maybe it's nearby or something, and we can sort of triangulate or average or something. Um, but yeah, that's all you need. So there's two outputs that come out of here. Well, there's more outputs than that. But if you click on the output port here, um, you'll see there's this value E, and I don't remember why I provide E, um, because I don't remember what E is. But we'll get back to that. The main output is all of those variables, which we don't really care about, really. You probably don't need those, but it's really the snow water equivalent that you're looking for. Oh, E is excess. Oh, that's what it is. Okay, E is very important. E is the main output. E is the excess water. And so this is essentially what would be your equivalent to looking at runoff entering essentially below the snowpack. So, and it worked. So you might be wondering, well, how do you integrate that with a runoff model? And I just put the the excess water as input, because this also includes rain. If there's direct rainfall, um, excess water includes that. This is excess water is it's the snow melt and the rain, all the runoff coming off. But it's we don't want to call it runoff because um, we haven't run it through any kind of process to represent the attenuation that happens in the watershed and through the soil profile. And over the overland or whatever. So I realize there might be some differences, right, in how you would maybe treat a watershed that is compacted with snow on top of it. But it does seem to calibrate fairly well. And so you're welcome to try it too. I'm curious to know. I'd love to have feedback from you if you end up using this. But the E is what you would then connect um, to look at runoff going on in your watershed. So that is the also this excess runoff. This is by zones, right? We had zone 1, 2, and 3. So um, let me just go back and show you uh, how I connected that, because that's kind of weird, right? That doesn't really match up with one point in the river. Okay, so I'm going into this model here. So snow 17, I go in there and I have excess water. And this, if I right click and do effects, I can see that it's affecting this thing called precip, which is probably inside of the runoff model. I am. I'm in one of the catchments of the runoff model. So that's where the water's going. It's going from excess water over into here. And I can also double click on this line right here, and it says I have excess water going to CO1. That's my first catchment, catchment 1. And if I click on the next row, it says it's excess water going to CO2. That's the second catchment. So if I go into the watershed runoff model, I have these two catchments here. So please note, these are not related to the snow zones, right? I have 3 zones for calculating snow accumulation and melt, but I'm only representing the runoff of this excess water from the melt and from rain using 2 catchments. So they're different concepts. They're different conceptual models completely. And I've just got an interface between the two of just saying what's the excess water daily coming in. And so if I go into one of these, it's the AWBM model, which requires ET potential and precipitation inputs mainly. I mean, it has some calibration inputs right there, but for the most part, pretty straightforward. You just link up the ET and the precipitation. Again, you'd need a ET. How do we calculate ET? I calculated it because I had temperature data, um, but you could just have estimates or averages or something. It's usually not a major uh, impact. Well, maybe it could have an impact on. I guess it does impact the snowpack, but the temperature. I mean, you need the temperature for the snowpack, so you obviously have the ability to calculate evaporation, or at least estimate it roughly, which is what I'm doing. In my case, I'm calculating evaporation. Uh, oh, oh yeah, this is a little bit more. This is a more involved way to calculate evaporation using this FAO Penman-Monteith method. Um, this is on our library too. You can look it up and see what you think, but it's a little bit involved. You could also put wind speed in there, and I think also daylight hours. So there's a lot of inputs to it, but anyway, maybe that's going a little far. We also have some very basic estimators that all you need is temperature, I think. Maybe temperature and one other input. So that's a little bit more complicated one, but you could use simpler ones just to get a rough idea, but still be reasonable, I believe, especially because you can calibrate them. So anyway, oh, okay. So to talk about how we got from those 3 different zones. So what I do is for this first catchment up here, um, I just say, let's see, precipitation is a scalar coming from where? Oh, I wonder if I picked a zone. Did it pick a zone? Oh, ID. Oh, that's right. Okay. Then okay, that is what I did. I said I wanted to divide. Okay. Well, it turns out that I um, all I did was I just applied the zone 2 excess runoff to this catchment. I see. Okay, well, that's not right. That shouldn't be done that way. Actually, I think because I've got this catchment divided spatially in this way, I think what I would prefer is that I would find out what the relative fractions of area each of the zones, snow zones, represents, and then use that to calculate an average um, for the entire area here. And then I would calculate the average of those three snow zones. Well, okay, so unfortunately, I don't have that built in right now, but my hope is that by the end of the next webinar on Thursday, that I will have, when I post an example on our library, I can also put in there how I could get those averages and then lump that into a single area of this catchment that represents a different spatial area. Um, that would be an important part to put in there. And I wonder if I did that in my, I wonder if that would help the calibration. So I'll have to look at that and see. I'm assuming it would be, I'm assuming that would be helpful. Okay, so somebody asked, is the addition tied to the time step length? Oh, are you talking about when I was adding that value in the script element? Um, um, yeah, that was a kind of a contrived example that we've never used. I just wanted to show that it could increment from its previous value, but that would be it wouldn't be tied. Yeah, yeah, it was tied. That would be not a good way. Oh, but are you talking about just Snow 17? So Snow 17, is it tied to the time step? And that is a really good question. That is a really good question. Um, and since I'm not sure if I can answer that on the fly, but let me do my best let me investigate something. So we can go over here in the browser and select Show Element Subitems, and then open up this local properties. And then I'm just going down through the local properties to see which are being used in my model. And I can already see a bunch are being used. The ones that we would be concerned about, if we're talking about moving away from daily, would be something like day of the year or day of the month. These won't work. If I go to the effects on this, okay, yep, it's being used in the script. So we've got some run properties being used in here that won't make sense in some other instances of a run setup. If we had a 1 month time step, then the day of the month would be, I don't know what it would be, maybe one, or I, maybe just, I'm not sure. Maybe it'd be a one, but it'd be constant and it wouldn't change. So it wouldn't make sense. So in a way, it's tied. It's tied in those ways. But I don't think it's tied in a way that would hurt us necessarily. Besides that, what I mean is it's not tied to the time step length. So luckily, you can see here we don't have anything like that. Um, so yeah, I'd say loosely tied. It's not coupled. Like some cases, you might have an equation that says, some variable divided by time step length, and that way it's very much tied and coupled with the time stepping. But I think in our case, you can probably change it, and have a different time step, but you'd want to play with it, right? And make sure that all the calculations are doing the right thing. And how would you handle a day of the month? Maybe, there'd be just some questions you'd want to ask. Also, if you go to hourly, you'd probably want to start looking at having it change over the hours too. So, and right now, all we do is we look at the latitude and I think the month. No, we look at the day of the month. That's right. Yeah. But if you go to a sub daily, you'll have constants over the whole day for things like the temperature changing and stuff like that and what that affects. So anyway, somebody said, um, can you open the snow var container? Oh, okay. I was going into this. Yeah, I wanted to definitely show you this. So I need to carry forward these variables. There's these four variables, and they're tied up into the results of the script element right up here. And you can see their names up here, snow 17 variables. And I need to have an initial state, right? That's actually really important, especially if you're going to model starting right now and there's still snow high up in the mountains from last winter, right? Um, then you want an initial state that shows some snowpack in there. So it's important that we can have a starting situation, and so that's why I have this container over here. I cannot incorporate this container into that script. It has to be calculated up front at time zero. It is just an initialization essentially. So what you do is you say, well, what is the initial snow water equivalent starting at time zero when you hit go? In my case, I started at not a snow time. I started in October. So I'm starting it when it's before it starts. And so I said zero, but you could put in numbers here. And this is a powerful way to start. You know, maybe you want to do a forecast model of what's going to be our, runoff this spring or maybe next spring. Um, then you could have a starting value and then calculate how fast it will melt, for example. But anyway, if I'll go back in here, somebody asked they wanted to see in here. So I want to have a starting value for all of these variables that I carry forward. It's really not anything you have to worry about. It's just something I have to do. I need a starting value that's based on the initial snow water equivalent, because these are related. If you specify, you know, 10 inches of snow water equivalent, then that means that these other things are not zero, if that's the case. So I need to have a way to initialize these variables given this initial state of this one value. And given that one value, it tells me what the initial state of all those four values are, which then go into here, which is the whole reason I'm carrying them forward, is because they have to have memory as this calculation walks forward in time. So anyway, it sounds really complicated, but really it's just a way to have like a little storage space that carries it forward in time, those values. And it allows us to have a starting value of snow water equivalent. Um, okay, so I hope that helped. Um, okay, so somebody said inside the Snow 17 script element, is there some logic for determining if precipitation is snow versus rain? And does snow water equivalent in snow get accumulated over time, often only having measured snow depths to calibrate against? Okay, so yeah, let's go in here. Yes, it does. It does do all of that. So, and I don't know how well documented it is. And the cool thing, by the way, about this new version coming out is you can scroll with your mouse wheel, or if you have a touch screen, you can scroll in here with your finger, which I'm doing right now, which I don't think I could do before. But anyway, so if we come down here, let's see, data validation, no, run parameters, initialize the state, okay, right here. Um, okay, so it kind of walks you through, which is nice. It kind of walks you through things that it's doing. It's taking the inputs, temperature, precipitation, so forth. Down here, starting on row 70, we adjust the temperature for the different zones. So we do all that. Okay, and then we take the initial starting snowpack and we then calculate this thing called melt function. Here's the melt function. So it goes through and it calculates all these variables, a lot of them having to do with the season, the time of the year, obviously sensitive to being in the northern versus southern hemisphere, um, which is why latitude of the site is in play here. Okay, I think it should work though in any latitude. Anyway, okay, so we do those things to calculate melt, and it's this thing called MF on 92. Repeat for each elevation zone. Okay. Oh, here we go. Divide rain and snow. So here's the answer to your question, I hope. 97. Divide rain and snow. Um, um, it looks like if the mean air temperature for each zone, that's what Z is less than or equal to this threshold temperature. So we can specify these threshold temperatures, which we can talk about. They're outside here, um, but it just looks at it looks at the temperature. It's based on the temperature, whether it divides rain and snow, um, surface temperature in each zone. And then we have snow accumulation, and it probably only accumulates. It, yeah, it's a fraction usually, depending on the temperature. Yeah, right here. If the temperature of the new snow is equal to air temperature. Now I don't know exactly what temperature of new snow is. It looks like it's initially 0, but they change it. But anyway, it's based on the temperature. Um, so uh, then we have heat exchange, and now these are, again, it's a conceptual model. It's not a physical model, but these equations do kind of, and you can read about it in this documentation, this Anderson document down here. They mimic the physical processes with these equations. So it's like empirical equations. Um, Ripeness of the snow cover, limits of the heat deficit. Um, I really like this one a lot better than the the other one we have on our website, um, the one that was by the USDA, which is also great for certain reasons, but it requires that you put in a curve, a snow melting curve in there, and it's just not very practical. I don't think it's hard to do. So I really like this one. Um, but anyway, I hope that answers your question. Okay. And then somebody asks, what do you adjust to get your calibration? Oh yeah, good question. I think I did use optimization. So let me go back to that other model, the calibration one. Honestly, it's been a while since I ran the optimization, um, but let me open it. Run optimization. So my objective function was an R squared. So yeah, I could probably pick some better ways now of doing now looking back on this to do calibration. I just looked at the closeness of fit with R squared. So there's probably a couple other things I could look at, especially if I was interested in the peaks and not so much the low flows. But I had some required condition in here too. Um, oh yeah, you get some really strange, like for example, the AWBM runoff model. You never want K. Well, it wouldn't usually make sense for your base flow to be a flashier, faster, spikier flow than your surface flow, right? It'd always be the other way around. So anyway, I didn't want them flip-flopping. I didn't want my base flow to be the spiky, peaky flow, and the surface flow to be the drawn out, long, smooth one. Um, and so I wanted to make sure that if I'm changing that variable using optimization, that I stay in bounds that makes it more realistic. Um, so is that just a hydrologic calibration? No calibration of the snowpack? That's a good question, because really I should have just been focusing on the springtime. So I should have just cut out everything else and just looked at the springtime. And I was calibrating not just the snow water equivalent. I was calibrating the runoff during the spring runoff melt, the snow melt runoff. So it was incorporating both. And I'm not sure if does this model have, this one does have observed. So let's just run the one that comes from our website, off our website. So this is just the snowmelt model by itself, and I do have observed records for a location that is, does it say? Well, let me get back to that. Let me see, snow water equivalent. Here we go. Um, okay, so here is the gauge is blue. Sorry, red is the observed, but the the gauge is located at approximately the the mid zone, zone 2. And so I'm just comparing zone 2. It's pretty close. It's not exactly that average elevation, but it's close enough. And so I'm using zone 2 output, and ideally maybe you would do an averaging method to get exactly the right elevation and measure and calculate that compared to the observed. But I was pretty close, so I just did it there. Um, so this is zone 2, the dark blue line. That's zone 2 compared to the observed snow water equivalent. And the question is, can you optimize this to get a? And yeah, I think so. I don't remember if I did, but let me just check to see if I have any optimization things saved in here. Okay, it looks like I tried it at one. No, that's AWBM, so that's not it. I I mean, yeah, we should try it. What are the things that we would play with? Um, uh, that is a good question. Um, yeah, we could play with these. There are some um, there are quite a few constants, and I'm using defaults, and so yeah, first thing we'd want to do is do a sensitivity analysis of these. So it means you'd have to put a data element out here. Um, Let me show you what I mean by that. Let's take, for example, well, let me just make sure I've got another comment coming in. Yeah, what parameters would you adjust? Great question. Well, here's a good question. Why don't we try, um, let's try a couple. Let's try lapse rate. That seems like that's important. Um, so I'll put a data element out here called lapse rate. They have to, anything that you're going to optimize on or do a sensitivity analysis for, it has to be out in a data element. So I'm going to put one here, and I'm pretty sure it's in C degrees, because you have to put the DEG for an incremental temperature. That's a temperature differential. That's different than temperature differential per meter or something. I can't remember. I need to go look. Um, Degrees per 100 meters. So they're saying it's 0.008 C degrees. Okay, 0.008. Okay, and then you would plug that in over here, right? So we would put that right here. And I'm not putting the tilde symbol. I realize these have the same name, but don't forget that to refer to something inside the script, you have to use this symbol. And then I have a thing called LAT in here, but if I just type something without the tilde, that's outside the script. So this is probably a little bit bad form, right? You shouldn't do this. They are different things. They represent two different elements. One's inside here and one's outside. But anyway, um, so now that I have that outside, now what you can do is you can say, what is the impact of this on the cumulative excess water runoff? Let's just do that because I have it available right now. So we'll come up here and we'll go over to sensitivity analysis, and then we'll click on cumulative. Whoa, oh, hold on. This is this is a vector. I need it to be this is excess total for zone 2. And excess water 2. Okay. Um, oh, my apologies. I need this one. Okay, and this is in millimeters, but it's millimeters per day. So there should be a per day. Is that what I'm doing over here? So here's another case where it's built in the time step, right? If you were to do an hourly model, you'd want to make sure if your output represents a value that occurs over a period of 1 hour, then this would have to be changed. So yeah, it is dependent on the time step, at least in these outer realms out here. I don't think it's so much in the script itself, but out here it is. Okay, so this is going to be millimeters, and then the rate coming in is excess total zone 2, and it is divided by 1 day. Okay, so we can see the impact on this total by changing the lapse rate now. So now I go over here, and I'm sorry this took so long, we're out of time, but that's okay. Okay, so here's the total excess from zone 2, and then I want to add the lapse rate here, and I'll have it range from 0.04, whoops, 0.04 all the way up to, let's say, 0.01, something like that. And then you can hit this plot button over here, and what it will do is it will show you, based on all the different runs, the impact it has. And you can see here that it doesn't have an impact. So right off the bat, we'd say, okay, either there's a problem and we need to investigate this, or this doesn't impact that output. Therefore, we don't want to include this in our calibration, right? So that would be the process that I would go through to find out which ones you would adjust to do a calibration. Obviously, you wouldn't adjust things like latitude, obviously, but maybe some of these others down here, we could look at them. Some of them are probably really important. Maximum melt factor after June 21st. I mean, that's right. That could be different everywhere, and that could be different in time. So there's some things in here that you could obviously zero in on, but you'd want to do a sensitivity analysis to find out which ones are making the impact there. Unfortunately, I picked a bad one. Only if you change the elevation on that one. Yeah, you're probably right. You're probably right on that one. That was a bad decision to pick that that particular input. But essentially, I would say the workflow should be um, find the inputs that you make a judgment call, right, and say which ones do you think would be a good influencer to the model and make sense to adjust. And after that, do a sensitivity analysis of them, and then you can see, oh, if they don't really impact, well, let's not do that, because you don't want to start adding too many optimization variables when you do a calibration. Hopefully not more than just a couple, maybe 2 or 3, maybe 4 at the most. Otherwise, it gets kind of hard to find a solution. That's been my experience anyway in it. So anyway, we're out of time, but oh, the sensitivity plot function. Okay, yeah, and I really feel bad because the sensitivity is not very interesting right now in this case. Um, and I don't really have time to build another one, but there's this button over here called plot. And if you click on this, it will run the model as many times as it says points down here. So you can have it run more points, but it runs 11 times, starting at the lower bound, ending at the upper bound, and it runs 11 times right in between with a central value where you specify. So it'll run at one time with just this, everything else held constant, and then run the next increment and so on. And then you can look at a tornado chart, which will show you the impact of all the different variables on the model result, this model results, in comparison with each other, normalized on a normalized graph. So the relative impact, which is nice, you can see their relative impact on the model results. So the tornado chart would be a good one if you're comparing multiple. So, all right, I hope that's useful. And thanks a lot for joining. Thanks for sticking around. Hopefully that's useful for you all. And please do let me know if you have questions or trouble doing your own calibration with this model. I hope it's useful. And again, like usual, I'll post an archive of this video on our website. And I will also provide links or downloads to the for the example models I go through. Thanks a lot for joining. So, all right, have a good one, and we'll talk later. Oh, also, by the way, we are thinking of doing a user conference um, next year. 2024. So if you have this, now's the time to um, put a ring in the hat, as they say, on where you want it to be. But it's probably going to be Seattle, but um, you should come to Seattle. So anyway, we're looking forward to that, and hopefully, and looking forward to seeing all of you. All right. Thanks a lot. Bye.